All right, today we're going to take a look at mathematics, and we're going to use the knowledge framework to kind of understand math as an area of knowledge. So we're going to break down step by step, starting with scope and applications, kind of defining what math is and how we use it, concepts and language, understanding the basic ideas and rules, methodology, how is new knowledge formed in math, historical development, how has that change happened over time from ancient Greece to today, and then links to personal knowledge. How can we connect personally with math? And then these knowledge questions are the types of things that you can play with in your math class or your TOK class. Starting with scope and applications. So kind of why math? What math? And so what is the social function of mathematics? Why do humans create math? Or is math created at all? Is math discovered by humans? Big idea is that math helps us understand patterns in the world through models, and that we may identify patterns that exist out there. And we want to put a name to it. We want to be able to write it out and better understand it through a model. And that this mathematical phenomenon may be huge, massive, and we want to be able to shrink it down to something that is understandable. And so we're going to do this in varying ways. Because there's lots of different patterns in this world. And so if we want to better understand business, we're going to use calculus. If we want to build things, we're going to use some geometry and understand how to best build things. If we want to communicate better, trigonometry is going to be the way, with radar, sonar, GPS. If we want to look at our data, measure and analyze data to make future predictions, that's where statistics is going to come in. And so all these different things are looking at patterns and trying to understand these patterns better. Math is tricky in that it is tied to certainty. More than any other knowledge, this idea that it is an absolute truth. Math is math, and you can't mess with it. And so that makes math beautiful, and that it is not up for interpretation. 1 equals 1, you can't mess with that. And it doesn't change. 1 equals 1 for all time forever. And so that's universal, that's timeless, that's beautiful for people, it's comforting for people that you can't mess with that at all. It's also terrifying in that you are kind of locked in. You can't interpret it in a different way. There's only one answer. And so when you come up short in your answers, it can be incredibly frustrating in that you made a mistake, that the flaw is the human and not the math. And so that's what frustrates a lot of people, is the absolutism of certainty in math. There are two main types of math, pure and applied. And within them, there's about 13 little substeps, or little branches. First is pure mathematics, and they are the ones that are looking at these kind of big abstract ideas, and they're finding new theories, at least mathematicians in these fields are. And we can certainly use them and apply them, but when we're looking at most of these ideas, we're not really in the real world necessarily. We're in the abstract, we're using pure reason outside of reality. And so we don't have to include all the little factors of reality, just the absolute rules of our systems. In algebra, calculus, geometry, we're just playing with those rules and seeing we can make new theories based on the common set of ideas that we all share. Applied mathematics, well, that's a bit different. That's when we're going to start to use the above theories and try to apply it to the real world, try to use them in new ways. And it's going to get much more complicated as we start to actually move beyond just those rules and try to get into the real world. And so this is where we get into things like physics, computers, statistics, human behavior, and all that messes it up a little bit. And so we get very different branches and layers of complexity in these different forms of math. Right? To what extent is math dependent on the culture? Not a ton, because it's pure reason, pure truth. Math is math pretty much across the world, across humanity. Almost all societies encourage math as just a basic thing, and modeling these weird abstract patterns that we see is a part of the human experience when it comes to counting things, trading things, calculating. It's a human thing, and we can see this whether that's in Egypt, Egyptian culture 5,000 years ago, or today. It's still just a necessary part of living. The rigor of mathematical pursuit, it depends on the individual, rarely on society. So largely, this is an individual experience when it comes to how good at math you're going to be. How do we use language in math? Well, the big idea is that symbols will vary across cultures, but the meanings of the symbols pretty much stay the same. And so we're going to use a precisely defined set of symbols standing for abstract things like sets and relations. However, and it'll vary by culture. Babylonians and Egyptians and Greeks, the Mayans, the Hindus, they're all going to have a slightly different way to write one, but the idea of one is the same. And so we're getting varying alphabets, but the idea did not change. It's just a different interpretation because these cultures may not have crossed over, may not have had contact. And so the Egyptians and the Mayans are pretty similar in some ways and as far as how they're coming up with their numbers, even if they never had contact. And so we see this human experience there. Unlike symbols, concepts are universal. And so, yeah, the idea of one doesn't change, but one itself, as far as how we write it, changes. But the basic ideas of how math systems work, all the same. We're going to have we're going to call it different things, but the ideas, same. And so for some examples, we all start with axioms. These are basically like a premise in logic. It's a starting point for reasoning that is accepted without proof. And that, as far as how circles behave, the idea that two parallel lines never touch is an axiom. That a line can go on forever, that a ray goes off in one direction. These are axioms. We're not going to look and try to figure out what that means. Let's just accept that as a starting point, as a matter of faith. We're not going to accept every little thing, but axioms, that's our starting point. Based on these axioms, we can start to figure out patterns. And from these patterns, we get theorems. And this is a statement that can be proved to be true on the basis of these axioms that we accepted, or we can kind of expand on and shift other theorems. Simple theorems can be used to construct more complex proofs. So Pythagorean theorem. We all know that one as far as how triangles work and the patterns of triangles, and that we can use that to kind of solve our problems because we understand the basic axioms of a triangle. And based on that, how a triangle behaves, we can get into theorems. Then we get into proofs, and this is a theorem that is shown to follow logically from relevant axioms, that I can prove it time and time again. It works every time. This is my proof. Conjecture, this is almost a proof. Not quite, though. And it's an idea. It just hasn't been proved wrong yet. It's so close. And so this is a hypothesis that appears to work, but we haven't absolutely proven it yet. And so some examples: Goldbach's conjecture, every even number is the sum of two primes. We have been working on disproving that for quite a while, about 100 years now. I'm guessing on that. And it is probably true, but we're not going to know for certain because we keep going and trying, and I think we're up to the millions of numbers, and we're going to keep running mathematical computer programs to figure it out, but it could be that the first million numbers, that's true, and then 1,000,001, it's wrong. And so we have to keep trying. And this goes into Gödel's incompleteness theorem, the idea that certainty in any system is impossible, that you never know, that there could be that 1,000,000th number that proves it wrong and it all falls apart. And so that's the tricky part with these theorems, is the numbers are infinite, and so we're taking it on faith that these theorems would work every time. And we hope that the certainty is going to keep going, and it's not going to be messy on that millionth try. Do the rules stay the same if we're doing different types of math? They do differ a little bit. In that geometry, we're dealing with lines and shapes. Statistics, we're using graphs and charts. Algebra, we're using new symbols and variables. So the rules do change a bit. And even if we're talking about very similar things, these are different fields and they're going to have different rules, different axioms, different theorems that they play with. And so the different forms are going to impact the language that we use, the axioms that we accept, and that may not all interact perfectly. Hey, which ways of knowing are we using? Not every single way of knowing we're going to be using. Reason is number one, because reason's all about that absolute truth, that absolute certainty, and we're trying to find patterns using these established axioms. And so reason is very similar to math in that you have your premises that you're established, and then you build on these premises to justify your reasoning. In math, we build on axioms to build theorems and proofs. And so reason is kind of number one. After that, we're going to use memory, and then we have to kind of look back and stand on the shoulders of giants, think about what axioms we're going to accept, what theorems we're going to build on. Faith, this goes back to we're not going to spend our time going through every axiom, every theorem, so we're just going to accept it and try to build on that. Intuition, that we have to quickly translate abstract ideas in order to communicate with another. We're going to have to estimate sometimes and kind of do those quick maths and use the back of our brains to intuitively think of the answers. Imagination's a huge one, and that we do have to have an imagination. Normally we don't think of math and imagination, but they need to work together. And because we're not going to come up with new ideas, new solutions without imagination. And so we have to visualize these patterns in our heads. And then language, there is a set of established symbols and rules when it comes to mathematics. They do have kind of their own language. And so there's bits of faith and imagination and language that normally you wouldn't think of in math, but it's essential for math. History. So how has math changed over time? The basic idea is that the new is always building on the old. We're always taking these old ideas and building a little bit more. And so that's why you kind of have to take math in a certain order. You can't just jump ahead because you're going to skip over a lot of axioms that you need to understand new theorems. And so major developments are going to change the way we see the world. That we can start with numbers, but then a big idea like zero can change things. A big idea like negative numbers or imaginary numbers, fractions, can really shift our thinking. And we can see tons of examples here as we go from just a simple counting up to geometry. Then we're getting into, again, calculus, exponents, roots. Then we're getting into linear algebra, and so it just keeps advancing. Riemannian, Boolean algebra, information theory, logarithms. It keeps building as we come up with all these new ideas that are going to build on top of each other. And each of these concepts are going to impact other areas of knowledge, and that science and math are married absolutely, and they need to work together. But then the arts are going to jump in as well, as we can discover new ways to play with color, new ways to look at color, and we can measure color mathematically. Music theory ties very much with mathematical theory, and so if we can look at how to measure sound in new ways, we can create new sounds. Role of math, how has it changed over time? And again, kind of building on that's the idea that it's constant change. And always building on the past theories, challenging them, and maybe changing them a little bit. And so, for you, it's a core field of study, but it's also a major field of study in the world. And the mathematicians themselves develop previous knowledge and new mathematics to serve new purposes, and that we may build some new theorem and have no idea what it is for, what we're going to use it for, but then 50 years down the line we may come up with a way to use it. And so we're trying to find patterns in the universe, and we may find a pattern, but we may not be able to use it right off the bat. And so 250 BC, Euclid in ancient Greece is developing plane geometry. Basics of geometry starts with Euclid. And then a little while later, we're looking at the ideas of ellipticals, that not everything's going to be on a flat surface. And then we get in the 1600s the idea that planets aren't necessarily going to go in a certain circular pattern. It's going to be elliptical pattern. And it took 1,000 years to kind of connect an elliptical theory into, oh, that's how the planet works. And then 250 years later, Riemann in Germany decides, I'm going to mess with Euclid, I'm going to reject ancient Greek geometry, and let's come up with the idea that we don't exist on a flat plane. We exist on a sphere, so let's play with geometry on a sphere. And so in this case, parallel lines are not going to exist, in that parallel lines will always cross if you're on a sphere. And triangles will change their behavior on a sphere as well, that we can have two 90-degree angles all of a sudden in a sphere. And that's a huge idea that's going to later on develop with GPS and modern mapping. But then Einstein picks up 65 years later and says that's going to work when it comes to gravity, and that gravity behaves in the same way, and we get the idea of general relativity. So we can see how each generation is building and challenging the previous generation. So how are you involved? Well, you're going to learn mathematics inside and outside of school. In school, you've got your math, but also your science classes that you're always using maths. Outside of school, you're going to be calculating everything with numbers. Whether it is instinctually when you're driving and just look at the speedometer, when you're shopping, you're thinking of these numbers. All areas of knowledge, you're going to be using math in some capacity. And you can come up with your own examples there. But even in nature and the idea of aesthetics or beauty, we're thinking of math. And the Fibonacci series is one big example where it's just a formula. 1 plus the previous two numbers, 1 plus the previous two numbers. And so the example of the Fibonacci series is 1, 3, 5, 8, 13, 21, 34, 55, and we get this golden ratio of 1 plus the previous two numbers. So 1 plus 1 plus 3, 5, and kind of building on from there. And so it's this basic idea that we can chart it out, but then we started to see it in nature, and we found a beauty and a comfort in this pattern that we keep on seeing. And so even just a mathematical pattern, we're finding beauty and comfort in it because we keep seeing it over and over again, and it is a comfort. Mathematical ability, and so how is your perception of the world and your position in it affected by math? A lot of times, mathematical ability is a proxy for intelligence, the idea that if you're mathematically smart, that means that you're a smart person. And there are consequences for self-esteem in that you could be an amazing poet and not be too great with your mathematical intuition. And so that can mess with people's self-esteem a little bit, in that we are putting all our eggs in one basket, that if you're good at math, therefore you're an intelligent person. And that just may not be so. And we can't measure a person's brain based on just one thing. But sadly, that tends to be the way it goes. And that we can look at that with our major, like the SAT, ACT, it's going to be math and English. And that's how we're going to figure out if you're smart. Big knowledge questions that you may play with in your classes. One big idea is math discovered or invented? Are we discovering these theories that they're out and that we're just plucking them? Or are humans inventing these ideas? Were they there before us? Right? Or are they there because of us, these theories? Right? Where does math come from? And so you can play with each of these in your own time, but that should be it. And that's math.